are known as semiconductor devices. Now, the chapter of the electronic devices or semiconductors is a bit difficult and hard to understand. My suggestion to you, if you want to study this properly, is first focus on the fundamentals of what is, if you see your books, the band theory. Okay, so the band theory is very important to understand. So focus on the band theory of solids. This is step number one, if you want to learn it. So the band theory of solids is the first thing that you learn in semiconductor devices. Okay. The second thing you learn is about the types of material, and this distinction should be clear in your mind, which is the distinction of what's a valence band. Okay, what's a valence band? What is a conduction band? What is a conduction band? What is a valence band and conduction band? Okay, and once you are comfortable with these two concepts, which is the concept of band theory of solids, the classification of material, and then you get into detail of within the band theory you have valence band and conduction band. These two should be very clear to you. Today I am not going to talk about these two, but what I'm going to do is dwell on the type of semiconductors, which is the intrinsic semiconductors and the extrinsic semiconductors. Okay, intrinsic semiconductors and semiconductors. You can only learn these if you're clear about the band theory of solids and you're clear about the concept of valence band and conduction band. Now, if you look into the words like intrinsic and extrinsic, intrinsic semiconductors, if you talk about intrinsic, these are essentially the pure semiconductors. Okay, pure semiconductors. And what you have is extrinsic is essentially what is called as impure semiconductors. So these are impure. Okay, so that's a classification. And then there are two types of impure semiconductors. So one is your N-type, the other is your P-type of semiconductor. Okay, now what we will do is we will try to understand some basics of semiconductors. Obviously I'm not going to get into the band theory and types of material. What I'm going to focus on is the definition of semiconductor probably, and maybe explain the intrinsic and extrinsic semiconductors. Now let's talk about the intrinsic semiconductors. Now if you look into semiconductors, so I said it's a bit hard to learn this. Now if you look into metals, for example, which are good conductors, they follow Ohm's law. There are limitations, and so Ohm's law, the voltage, if you look into a V versus I graph, it's a straight line that you get, which represents the slope is equal to V by I, right? And this is your Ohm's law. But in the case of semiconductors, this is not true. They don't follow this law, which is Ohm's law. Okay, so semiconductor devices or semiconductor material does not obey Ohm's law. Okay, so semiconductor devices do not obey Ohm's law. Okay, this is one thing. Now let's talk about the concept of intrinsic and extrinsic semiconductor. This is just some general knowledge for your benefit, that semiconductors do not obey Ohm's law. So if you see a situation where you have semiconductors, don't try to apply Ohm's law to those numericals or situations. Now let's talk about intrinsic semiconductors. Okay, now intrinsic semiconductors are the for example, what you have is the silicon and germanium, okay? These are two pure semiconductor materials available in nature. And if you look into the periodic table, you will see you have carbon, you have silicon and germanium, okay? Now, if you look into the, these two, which are classified as pure semiconductors, they have, a structure like this that, a silicon, probably has, if I draw the electronic configuration, of silicon, this is the way it looks like, okay? So I have, two electrons here, and I have 1, 2, 3, 4, 5, 6, 7, 8, and so I'm left, so this is 14, and so 2, 8, and 4, 1, 2, 3, and 4. So these four, which are outermost, on the periphery, so let me just focus on, this, and this. So this is 1, this is 2, this is 3, and this is 4. So these four are the outermost electrons, and germanium too has 4 outermost electrons. And what these do is these two elements, what they do is they create covalent bonds with the neighboring atoms. So, if you pick up one silicon, what you do is you have a neighboring silicon, which is also, which is 1 and 2 and 3 and 4, so you will have 4 covalent bonds being created. So each of the electron, participates in formation of covalent bond. So what you have is a situation of covalent bonds, and you have 4 covalent bonds, which are sharing of the electron being done in silicon and germanium both. So this is the speciality. So you will see some diagrams in your books where, you have a silicon, atom surrounded by 4 more, 2 and 3 and 4, right? So you have this bond, and you have another bond, and you have another bond, and you have another bond, okay? Now these silicon and germanium, which are part of the intrinsic semiconductors, they create these kind of bonds, and these are covalent bonds. This is a covalent bond, a covalent bond, covalent. So you got 4 covalent bonds. And what's so great about this is the fact that the way they're organized by nature, is the structure is called as a crystal lattice, okay? It's called crystal lattice. So all the silicon atoms, the way they're connected to each other, you will see the diagrams, which are in 3 dimension. You have silicon here, and so it's a 3-dimensional structure. Crystal lattice is the exact word. So this is special characteristic for silicon and germanium, and many silicon and germanium atoms are going to form covalent bonds with each other. And the way they're organized, all across, they constitute what is called as a crystal lattice. Now, if you look into that crystal lattice, what you find is that the number of electrons available for conductivity is very, very low, okay? Which is the charge carrier, right? In metals, you have abundant electrons, but in the case of this covalent situation, the bonds are very stable, there is absolutely, no availability of electrons, although electrons can travel within a crystal lattice. If you have a crystal lattice, the electrons are capable of traveling through the, electrons are capable of, moving within the crystal lattice. So electrons can move within the the lattice, and however, the conductivity of these type of semiconductors is pretty pathetic, right? So you really don't see them in practical application being used that frequently, and and therefore, we have to do something special to increase the conductivity of silicon and germanium. So pure semiconductors, which are silicon and germanium, are poor conductors of electricity, and really, in terms of application, real life applications, don't contribute to a lot towards that. And therefore, what you need to do then is to follow a process called as doping. Okay, so let me talk about the process of doping. Okay, and this is very interesting thing to do. Okay, so what you do is you pick up a pure semiconductor like silicon and germanium, and then what you do is you dope it with some other element. So this other element, there are many examples, and there are two types of dopings you can do. Now, what you've done is you've picked up a pure semiconductor, and this is doping. And what you've done here is you've ended up creating something which is an impure semiconductor. So this is your impure semiconductors. Now, this impure semiconductors, I told you these are of two types. This is N type and P type. And these get created based on what type of doping you used. So if you use a doping which is you can have two types of doping. So let me write the types of doping which are possible. So let's say the type of dopings. So I can have a pentavalent, and I can have what is called as trivalent. Okay, so these are the two types of dopings I can do. If I do a pentavalent doping, what I get is an N type of extrinsic semiconductors, and if I do trivalent, I can get what is called as P type of semiconductor, which is extrinsic, impure, but the impurity which you add is trivalent. And you can have examples. For example, if you add something like arsenic. Okay, now arsenic is pentavalent. Okay, and this will fetch you an excess electron. So it's a donor of electron. Okay, and what you can do is you can add gallium or boron. Those are trivalent impurities, and what you end up getting is a p-type semiconductors. And you will be astonished to see that if you add one impurity atom per million pure atoms of silicon or germanium, you will see an exponential rise in the conductivity of the semiconductor. So an impure semiconductor is an excellent conductor, not like metals, but it is still somewhat close to being called a good so it's somewhere between metals and insulators. But when you add impurity, there is a tremendous improvement in electrical conductivity of the pure semiconductors. Now, this is something you must understand pretty clearly. And when you go deep inside this topic, you have to understand this topic from the standpoint of view of the energy level of donor level, what is the energy of an acceptor level, why upon addition of impure atom like arsenic or boron, which is trivalent, why there is an increase in conductivity of electrons. So understand the energy diagrams, understand the process of doping, understand the diagrams that show you how the bonding keeps on changing. In the case of P, which is P is positive. So what you end up getting is creation of excess holes, but in the case of N, what you end up getting is excess electrons. Okay, so what you get here is excess electrons. Okay. So hence the word N. N is negative, and P is positive. Not that they become positive, but in a virtual sense they do. So semiconductors, one important thing I want to tell you was that semiconductor devices only conduct in one direction. Okay, they don't conduct in both the sides. For example, we would see something like diode, okay, which is an NP diode, and you connect a battery to this, this will not conduct in both the directions, okay? So the way these semiconductor devices conduct current is, or the flow of electron is unidirectional. It is not bidirectional, okay? And so there are many things you can learn. Once you are clear about the band theory of solids, you understand the types of material, and you understand the energy diagrams, of our valence band, and then you understand the distinction between intrinsic and extrinsic semiconductors, who's responsible and how. For example, in the case of trivalent, you have holes which are responsible, in the P-type semiconductors for improvement in the electrical conductivity. But in the case of the N-type extrinsic semiconductors, you have arsenic, which is responsible, okay? And then you have to go deep inside the energy diagrams and work through your way, as far as this chapter goes. You can expect a lot of questions, from this. Those who are pursuing, J, those who are pursuing your board examination, this is probably, one of the hardest topics to do. But the trick to overcome this, if you find it hard, is to go deep inside this topic. Do some research, take up a few books and read NCERT for sure, because NCERT has given a lot of good detail on, the band theory of solids and stuff like that. So I hope you found this useful, and I conduct live classes. My number is given in this video. I welcome you to join them. If you're somebody who's inspired, you want to score very well in your board examination, want to get a good rank in NEET and JEE examination. So thank you very much for your time today, and I look forward to, make another video for you. So thank you very much. Have a good day. Bye-bye.